So what do we do with this one? That's this. In order to find x bar, how do we do it for center of mass? What are we summing up? The masses. Sum up the mass times the distances and divide by the sum of the masses. How about with volume? What do you do? Are you getting the trend? With weights? So the critical component is important. In order to find the center of gravity, which is, these are all distances, right? In order to find the center of gravity, we know center of gravity has a critical component of weight. We sum up the weights times the distances divided by the weight. For center of mass, the critical component is mass. To find the distances, we do sum of the masses times the distance divided by the total mass. What about volume? Sum of volume divided by
Volume.
sum of volume. And how about the centroid of area? How do I find this?
Area.
Area.
X, Y. Sum of area.
And I just solved for x bar, right? Is there a y bar? In this particular example, there was an x distance and there was a y distance, right? We were looking at forces going down. There's an x and there's a y. Okay. So let's look at the problem. So everybody should have gotten this. We're looking at this. And we are going to solve this using tables. Let's read the problem. Locate the center of gravity. Up, center of gravity. What is the critical component?
Weight.
Weight. Sure enough, that's what they gave us. So what's the weight of A? 25 pounds. Weight of B? 35 pounds. Weight of C is 15 pounds. Weight of D is 28 pounds. Weight of E is 16 pounds. Let's set up a table. So first is, what body are we looking at? Body A, B, C, D, and E. Next column, the critical component. What is the critical component in the center of gravity problem? It's weight, and it's in pounds. So what's A? 25, 35, 15, 28, 16. And let's do the sum at the bottom. What's the sum of that? 60, 75, 85, 95, 105, 105, 119? Is that right?
Yes.
Okay. And now let's do x bar, which the distance is in inches, right? So where do we want to measure the distances from?
The origin.
The origin. And it's a 3D problem, so we can't get confused, right? So where's the x-axis? It's coming out at us. So let's go around the room. David, let's start with you. So for A, what is the x distance from the origin?
10 inches in the x direction.
10. Okay, how about next, B? What's the x distance?
Also
10. C?
0.
Good. D?
10.
Mike, are we up to you? From the origin, what's the x distance to D?
11, 10.
10 over 1.
10. And then E?
0.
0. Okay. And now let's sum up the weights and the X bars. So what unit is that going to be? Inch, pound. Is everybody's looking at what I'm doing, right? So what's that? 250, 350, 0, 280, 0. And what's the sum of that? 600, 780. So what is X bar going to be equal to? It's the sum of the weights times the X bars divided by the sum of the weights. So it comes up to be 880 divided by 119, and that turns out to be 7.4. Does that make sense? Along the x-axis, we see A, B, and D at 10 inches away, and E and C were at 0 inches. If there was another particle at 0, where would the center have been? Okay, I'm going to say it again. Everybody look at the picture. A, B, and D are all 10 inches from the origin. C and E are 0 inches from the origin. If there was another particle 0 inches from the origin, where would the center of gravity have been for those 6 bodies?
5.
At 5 in the center. Now, am I finished? Did I find the center of gravity? I found it only in the X, right? In this problem, you guys, in this problem, we were looking at a 2D problem. I needed an X distance and a Y distance. But what kind of problem is this? A 3D problem. So what do I need to do? I need to find Y bar and Z bar. So let's do what? Inches. So Brandon, we're up to you. A.
0.
0. B.
11.
11. Right. Next, C.
16?
Yep. D.
16.
Right? And E?
Zip.
0. Okay, so the sum of the weights times the Y bar. Inch, pound. 0, 0. I'm sorry, wait. Well, I'm sorry. Yeah, 0. Okay, so I just got messed up, so that means you can't mess up. We're multiplying the Y bar times the weight. So it's 0 times this. What's 35 times 11? What is it? 385? Is that right? Okay. What's 16 times 15?
40.
Thank you. 16 times 28?
48.
448. And 0 is 0. And then what's the sum?
1073.
What is it?
1073.
1073. So Y bar is going to be 1073 over 119, which turns out to be
9.
9.0 inches. Does that make sense? 9. So looking in the y-axis, these two are at 0. These two are at 16. This is at 11. Yeah, it's about right. And then let's do the next one. So now we're doing Z bar. And A, B, C, D, E.
Drop the page.
Oh, thank you. So what is Z bar? Where are we? Is it Lily? So we're looking at A for Z. What is it? 0. B? Alex?
You're talking about the distance from the X?
Yeah, the distance from the origin.
Okay. 0.
Right, C,
0.
D,
11.
yeah, E. Okay. So now it's weight times Z bar, which is inch pound. And the weight, so it's 0, 0, 0. 280 times 11,
308.
308. 11 times 16,
176.
okay, and the total,
484.
484. So Z bar is equal to 484 over 119, and it turns out to be
4.1.
4.1. So what kind of problem is this? Is it a centroid of area, a centroid of volume, a center of mass, or a center of gravity? Center of gravity. What's the critical component?
Height.
Weight. And we did it all with a table. These might be the easiest problems we do in statics. What do you think?
Yes. How do we state the answer? Vector form or?
No, you just leave it like that, X bar, Y bar, Z bar. You could leave it like that. I mean, you could put it as a coordinate if you want, but usually you just see it like that.
Cool.
Okay, now we're doing this problem. So the problem should ask you, there should be a question there. There is no question. What do you think they want you to find?
Centroid area.
Center area.
What do you think? So Spencer said centroid of area. Hang on a second, you gotta see that last number up on top.
Centroid.
Do you think centroid of area is right? Why?
This is the only components we have are X and Y.
The only thing they're giving you is distances, right? They're not giving you mass. They're not giving you weight. They're only giving you distances. So it's got to be something to do with geometry. And it's 2D, right? If it's 2D, so if it's geometry, you know it's centroid. If it's 2D, it's got to be area. So now we have to figure out, this one was easy in knowing what the area, the bodies were. They were A through B, right? And here, we divided, this is very similar. We took this distributed load and we divided it up into two. Looking at this geometry, talk to the person next to you and figure out how you want to divide this up. What sections do you want it to be divided up into?
Two triangles and a rectangle. Two triangles and a rectangle.
Yeah, that's a hole. So you guys, this is
Assume
so
it's
you guys, let me interrupt you for a minute. This is a piece of metal. And it has a hole in the center. So it's really only one part. But, and if you look at it, this is really just one distributed load. But we sectioned it off. This is one metal part. But in order to find its centroid, which we need to know for mechanical design or civil design or aerospace design, we have to divide it up into parts. Okay, so talk to the person next to you and figure out what you want to do. Okay, how many parts?
4.
4. The red. The green. The blue. And then let's use black. So what are we gonna call it? How about we, the red is,
Box one.
1. The green, let's say the blue is 2.
Blue two.
The green is 3. And the whole is 4.
Well, let's just come on there now, we can call that just center. Because it's exactly what the circle has. Is the center of the circle right there? So on the back.
Okay, so what's our first column? First column is whatever the sections are. So 1, 2, oh, we didn't use Roman. 1, 2, 3, and 4. And then what goes in the second column? Huh?
Critical component.
Critical component, which is what? Area. And it's in millimeters squared. Remember, write the units up on top. You only have to write it once. So what's the area of the first one? 40 times 70. Second one is 1/2
40 times 7.
times the base, which is 90.
No, can we go back to box 1 and how you got 70?
Oh, sorry, 120. Thank you. 40 times 120. Sorry. 1/2, 90 times 60. And 3 is 1/2, 30 times 60. And 4 is pi r, which is 30 squared. Do we have white out? Yeah. Yeah. No, you don't have to separate 2 and 3. You can keep them together if you want. So where would you find, well, actually, no, I would separate it. Because, well, for me, I know what the centroid of these two are in the y direction, but I don't know where this total thing is in the x. Right? On the blue triangle, I know it's 2/3 over and 2/3 over for the green. But I don't know where the x centroid is of the two together. Okay, what do you notice about, sorry, I should have made it longer, you know, for this area, because I have to do the calculation too. So the area is 270, 2,700 rather. 4,800. $100.
What?
480. Hang on, I'm sorry, I'm reading off the wrong thing. 900. 480, 2,790, and this is 2,827. Now, what do you notice about that circular area?
It's supposed to be negative.
It's got to be a negative, because it's a hole. So the sum is equal to 5,573. So what is the first column? First column represents what? The part, the section that you're dealing with. The second column represents whatever the critical component happens to be. What's the next? X bar. and it's in millimeters. So for 1, where do we want to draw it? Well, here, you guys, we have to, this could be our x-axis, and this could be our y-axis. So where are we measuring from?
The origin.
Watch this up here, you guys. If I'm measuring the x-bar, I could draw it like this. I'm measuring it from the y-axis or the origin. So where is it for the rectangle? 60. Where is it for this triangle? Blue, it's 2/3 of 90. So what's that? 60. Where is 3? It's 90 plus 1/3 of 30, so it's equal to 100. Then 4 is 70. Everybody okay? What do I put in the next column?
Area.
The sum, the area, times x bar. And this is what? Weird units, millimeters what? Cubed. So it's 60 times 4,800. It's 288,000. The next one is 162,000. Next one is 90,000. And the last one is 1,978,000. And remember, it's a negative. So the sum turns out to be 342,110. So what does x bar come out to be? It's the sum of the areas times the distances divided by the sum of the areas. So it turns out to be 342,110 divided by 5573. And x bar turns out to be 61.4 millimeters. Okay, is this a 2D or a 3D problem? So I need, and what else do I need besides an X bar? I need the Y bar. Y bar, millimeters. 40 divided by 2, 20. 40 plus 1/3 of 60 equals 60. Plus 1/3 of 60 is equal to 60. So once I get the Y bars, then what do I want to calculate?
H-wise.
The area times the Y bar, which again is going to be millimeter cubed. And it turns out to be 162,000, 54,000, negative 113,080. And the sum turns out to be 198,920. y bar is equal to the sum of the areas times the y divided by the sum of the areas, 198,920 divided by 5573, and y bar turns out to be 35.7 millimeters. So now, everybody looking at this figure, where do you think the centroid should be? So here's the left spot, here's the right, where's the middle? 160 is the middle, right? But here's where the hole is. The hole is over on the right side, so it's more negative stuff there, but yet there's more material there. So it's going to hover around here. What did we get for x?
61.4.
Okay, 61.4. Is everybody here why? Like there's more negative to the right side, but then there's more material to the right side. Okay, how about this? Let's bring this down. So here's the bottom and here's the top, and there's a lot of missing material up here, so it's got to be low. If there's a lot of missing material here, it's probably maybe somewhere around here. I don't know, maybe less than 40? What did we get? What did we get?
35.7.
Oh, we did. Got less than 40. So let's open up these problems. Okay, talk to the person next to you about it. You feel like you got it?
All of 7 is something. On the chart.
Well, mainly it's because we're on the could have been like forces or something, or 5 something. But because those dimensions, this area, the 88 thing, it was like density. My judgment might have been
Like, I don't think
Okay. Okay. Now we need to understand some terminology. Okay? So we're turning this over. Okay, so here are the center of mass, center of gravity, centroid of area, centroid of volume. So centroid of volume is 3D. Let's put critical component in the first row, first column rather. What's the centroid, 3D centroid critical component? You guys? Volume. How about centroid of 2D? Area. How about center of gravity? Weight. How about center of mass? Mass. And how about distributed load? Force. Going back to the distributed load over here, everybody look over here. We had a distributed load, right, that we made into a point load, and then we made to one force, and we were able to find the distance. How did we find the distance? We summed up the mass, we summed up the moment, which is really about summing up the force and the distance. So take a look at this. For centroid, we sum up the volume. Everybody say this with me. For centroid, we sum up the volume times the distance. And then divide by the volume.
Divide by the volume.
For the centroid of area, we sum up the area times the distance.
Area times.
Divide by
Area.
sum of the area. How about center of gravity? Sum up. Okay. So so for the center of mass, it's mass. And then I wrote center of gravity, replace the mass with the weight. Okay? All right. Here is where we have to know some terminology. let's look at distributed load first. I'm looking at this column. Everyone? When we sum up the forces times the distances, we're trying to find the moment of the force reference to point O. Does everybody agree? Look over here. We summed up the moment about point A, right? And it was force times this distance, force times this distance. We found the sum of the moments about point A. Everybody's comfortable with this? Okay? So it's the same thing on the distributed load. What we're doing is we're summing up the moments, summing up the forces times the distances, which is the sum of the moments about point O in this particular case. Okay, let's go to the area. Everybody look exactly where I'm pointing, because this is where the terminology is kind of weird, but we have to accept it. We summed up the area times the distance, right? And it was a 2D problem. So let's look, we look at this at the same time. We were trying to find the x distance. The x was referenced to what? The y-axis, right? We found the x distance from the origin, but we're really referencing the y-axis. It was the distance from the y-axis. So when you do centroid of area, when you sum up the area times the distance, it's referred to as the moment of area reference to the y-axis. Is it really a moment? No. Right? We know, everybody look at me, we know moments are forces times distances, right? In centroid of area, we're not multiplying forces times distances. We're multiplying what? Areas times distance. But they call it moment of area. So here, on the centroid, when we summed up the area times the x distance, it was the moment of area. And it was referenced to the y-axis because when we're calculating the x bar, we're referencing the y-axis. So what do you think then when we're trying to find y bar for centroid? Let me move this paper over so we can see what we're looking at. When we're trying to calculate y bar for the centroid of area, we're summing up the areas times the y distance, so it's still called moment of area, but it's referenced to what? The x-axis. Everybody got that? So it's the moment of area. So what do you think when I do center of mass? It's the moment of? Okay, so when I do centroid of area, it's the moment of area reference to something. When I do center of mass, it's the moment of mass reference to something.
What does that mean?
I'll tell you in a minute. But now, how about if it's a 3D problem? You guys, you can't go yet. When I was trying to calculate x bar, calculating x bar on this 3D problem, where was I measuring x bar from? The YZ plane. So when I have a 3D problem, here, in a center of mass problem that's 3D, here's 3D, I'm showing you a 3D example. When I'm trying to find x bar, I'm summing up the masses times x bar, but it's referenced to the YZ plane. What is it called? Moment of mass reference to the x. It's supposed to be YZ. I've never taught this error before. YZ, correct it, you guys. Yeah, the rest are right. It's just that first one. So everybody needs to tell me, when we are doing a center of mass problem, and it's a 3D problem, and I'm trying to find y bar, it's the moment of mass reference to what? XZ plane. And this last column here, the last column here is showing you how we would do the integration, but we're not doing integration. We're only summing them up the way we've done on tables. So what are we actually doing? Here, are we truly finding moments? Are we truly finding moments when we do moment about A?
Yeah.
Yeah, forces times distance. Here, are we truly finding moments when we deal with center of mass? No, we're multiplying mass times a distance. That's not a moment, but it is called a moment of mass. Right? So we have a mass spinning around here, and it's about this point. It's some mass times a distance. Can any of you see where we're going? Remember in physics? Moment of inertia? The distribution of mass, or the distribution of area, causes some kind of rotation. You had all these little demos in physics. So this is called a moment, just like moment of inertia. It's not really a moment as what we know, force times distance. It's related to this kind of moment. So here's a moment of mass, moment of area, moment of volume. Okay, let me end there. I need the clipboard that has already signed up for. What is that?